Okay, so we have y equals 40 plus x squared over 3, and we're ultimately going to revolve this around the x-axis, so that we're going to have a graph between x equals 0 and x equals 12, like this. It's going to get revolved in the third dimension around the x-axis, giving us a figure that looks something like this. We've seen this before. Okay, kind of like a horn. And we want to find the volume. Okay. Well, you know, first thing we do is, or first thing we did was we constructed a trapezoidal approximation graph in 4 intervals for this function. And you can verify that to the nearest 1,000, the areas of these regions are 5, 7, 11, and 18,000. So the accumulated areas are 5,000, 12,000, 23,000, 41,000. Those aren't going to be particularly relevant, but when you do a trapezoidal graph, you do that. And you would also have labeled the slopes. That'd be pretty simple. Yeah, this would be 3/4. Or no, this would be 1, it could be 3 over 3. Slopes aren't relevant. These areas aren't totally relevant, okay? But they're kind of relevant. Okay, well, then we come over here and we look at the same function between 0 and 12. But we're going to let this axis, well, it could still be the x-axis, but now we're going to use r for the x-coordinate. And we're going to have a width delta r here. And let me just double check the paper. Make sure that we're using that notation because okay, well, we use r and a delta x in the original, so we'll call that an r and a delta x. And I'm not going to do that. I'm going to call it x and delta x because it's not really what I'm talking about with r. Okay, so here's a typical x and a delta x. Now, if we revolve this segment here about the x-axis, we're going to get something that's pretty close to a disk. It's going to be somewhat beveled. It might look something like this. Not particularly well drawn, but you get the idea. Okay? So it's a disk of thickness delta x and radius plus x squared over 3. So its volume is about, well, we'll use the expression that we had for a disk of radius r and thickness h. Well, I'm going to say cross-sectional area times thickness. Okay? Now the cross-sectional area isn't quite uniform. The disk bevels a little bit. It's a little smaller on one side than the other, but we're assuming this is a very small delta x. So whatever x value in between these two endpoints we choose, we're going to use as a basis for finding the cross-sectional area. So that's going to be, well, radius of the disk is 40 plus x squared over 3, right? And then that's times delta x. Okay? So that would be the volume. Now, I'm actually going to call that a delta V. That would be the contribution to the volume of this disk. Okay? Now, if I just use this 4 trapezoid approximation, then what I have is 4 trapezoids, each of width 3, because 12 divided by 4 is 3. And the average altitudes, using the average altitudes. Well, this is 40, and this is 40 plus 3 squared over 3, which is 43. So this is 41.5, just as an example, okay? If I was to revolve this trapezoid around the x-axis, the volume is going to be what? It's going to be, well, 41.5. And I wrote this down again. It's pi times the square of this. Pi times the radius squared, right? Okay? So it's going to be pi times 41.5 squared times the thickness, which is 3. Okay? Now, what I'm saying then is this is the same as the area of the trapezoid and it's not really the same, it's nearly the same. Okay? Still using our 4 trapezoid approximation. So if I did a trapezoidal approximation graph for this function, I would have trapezoids whose areas represent the areas we would get by revolving the individual trapezoids. Okay? Does that make sense? So, this graph would approximate the volumes of the solid of revolution. When I say volumes, I mean the volumes of the solid of revolution for each individual interval of this graph. Okay? Then, if you start shrinking these areas, you get more and more accurate approximations to the volume of the solid. And that approaches the integral. Okay? For that reason, the exact volume x squared over 3 and it's squared. Okay? Now there are a lot of connections in here, but if you understand that, you understand a lot about solids of revolution. Ultimately, you're just then doing pi times the radius that you get from this squared and integrating that with respect to x. Now, if that's all you understand, and if you can do that, that's great. But then there's the question of what happens if you revolve around the y-axis.